Thanks, Pat. Thanks to the Royal Institution for having me back. This is one of my favorite places to come visit. And I thought that I would, in the tradition of Michael Faraday and Humphrey Davy and all the greats who have stood more or less in this place, begin the lecture by doing an experiment. Now, I'm a theoretical physicist. I'm not an experimenter, so don't get your hopes up too high. But I would like to do an experiment that illuminates the fundamental nature of motion. Okay, so you see here we have an object. It's a book. You can buy it in the finest bookstores everywhere. And we're going to observe what happens to the object. Nothing much happens to the object is the short answer to it. It just sits there. But I can, if I push on the object, get it moving. And then if I stop pushing, it stops moving. The nature of motion there being demonstrated to you right there. So if you were the kind of systematic thinker that, let's say, Aristotle was, you would go from a demonstration like that to a very deep picture of how the world works at a fundamental level. You would say that there is something called the natural state for the book to be in, which is just sitting there motionless. You could say that if you don't do anything, an object stays in its natural state. But if you apply a force to it, an impetus, you can change its natural state. You can cause it to start moving. And you notice when I then stopped pushing, it stopped. It returns to its natural state. So you invent what philosophers would call an ontology or a metaphysics, a fundamental view of what the world is made of. It's made of things that have natural states, and if they're not staying stationary and unchanging in their natural states, it is because something is changing them. When there is motion, there is a mover. And you can go from this simple idea to a theory of physics, as Aristotle did, and you can in fact go beyond that to a theory of metaphysics that explains not just the motion of things, but more or less how everything changes and transforms at all. You can even go all the way back. You can say, well, okay, this thing is moving because this other thing is pushing it, but what causes that other thing to be moving? If you trace the chain of motion and movers backward, you eventually would need to reach an unmoved mover and thereby prove the existence of God without ever leaving the lecture hall right here. This way of thinking is not only a systematization of some very simple physics experiments you can do, it also sort of accords well with our everyday experience. When you see something moving or not moving, it's because something is moving it or not moving it. So there became a philosophical tradition which tried to go from the physics of it to a deeper understanding, claiming that everything that happens, whether it's motion or otherwise, happens for a reason. This is not just a bumper sticker you can buy. This is a very venerable philosophical maxim known as the principle of sufficient reason. So here you have Aristotle, Spinoza followed up with his version of the principle of sufficient reason, and then Leibniz on the right, German philosopher who also invented calculus. They all put forward this idea that we can understand how the world works at a deep level by providing explanations for everything we see in it. Nothing happens randomly, nothing just happens. There's always a purpose, a cause, a reason why things happen. You might be forgiven for thinking that the ultimate purpose was ever more grandiose hairstyles for professional philosophers, even if Leibniz sort of had some artificial help there in his coiffure. The problem is that this is not right. The problem is that the world does not work this way at a fundamental level. There's two problems. One is it's not right. The other is, despite the fact that it's not right, we haven't abandoned it yet. So we have learned a lot about how the world works because of the progress of science and philosophy, but we still talk a language that is handed down to us by Aristotle, Spinoza, and Leibniz. Now, people have tried to fix the language. Here is Bertrand Russell, a more modern philosopher, trying to point out that the very idea of cause and effect is no longer fundamental in our understanding of the world. He says, the law of causality, I believe, like much that passes muster among philosophers, is a relic of a bygone age. Surviving, like the monarchy, he couldn't resist, right? Like, I'm just a messenger here. This is not I'm not saying this. Surviving like the monarchy only because it is erroneously supposed to do no harm. Now, many people would be surprised to hear the news that science has done away with the principle of cause and effect, but I'm not going to undo that. It's actually true. It's not that there's no such thing as cause and effect, it's that it is not a fundamental principle of how reality works. It is a very useful, helpful way of thinking about things at a macroscopic, what we will call an emergent level of reality, but it is nowhere to be found in the most fundamental laws of physics. And that difference puts us in the position of Wile E. Coyote, a famous American cartoon character. I don't know how popular the Roadrunner is in the UK. Good. So Wile E. Coyote, you will remember, if you're of the right age, had this thing that he did every single episode where he would run off a cliff. And because it's cartoon physics, not either Aristotelian or Newtonian physics, he would not fall down until he noticed that he was not standing on anything. He would look around and then, oh, and then he would fall down, okay? We are all Wile E. Coyote in some sense. And in the following sense, this cliff, this solid surface that we used to be walking on, is our old-fashioned Aristotelian et al. Notion of causes and effects and purposes and meanings in the world. We have left that behind. The fundamental rules of nature, according to our best scientific understanding, don't work that way, but we haven't adapted. We still speak a language as if cause and effect, purpose, and goals and reasons why are the fundamental way the world works. So one of our challenges should be to reconcile the deep down vocabulary of the world given to us by physics and modern science with what philosophers call the manifest image, the immediately accessible view of the world we have. After all, physicists love to make fun of Aristotle and say how wrong he was, but look, the book does stop moving, right? That's not a mistake. That is an accurate way of talking about the world. Cause and effect are accurate, useful ways of talking about the world. You can be accurate without being fundamental. Our goal is to show how at different levels of analysis, different levels of squinting at the world, reveal different rules, regularities, and even vocabularies for speaking. So I like to trace the origin of this shift from Aristotle to Bertrand Russell, for example. It's actually a long series of very, very interesting thoughts and experiments over hundreds of years between Aristotle and, let's say, Isaac Newton. And I like to give some credit to this guy, Ibn Sina, who sometimes Romanized or Latinized as Avicenna. He was a Persian polymath in the Islamic Golden Age, around the year 1000. And as a modern-day theoretical physicist, I find Ibn Sina extremely annoying because his day job was he was a doctor. His interests were in health and human anatomy, and he wrote many books about the human body. And on weekends, he invented new fundamental laws of physics. We can't do that anymore. It's more work now. The low-hanging fruit has been picked. So Ibn Sina was thinking about Aristotelian notions of motion and so forth, and what he pointed out for the very first time was that this idea that the book stops moving shouldn't be thought of as the book returning to its natural state of motion, because if the book was not on the table here in a room, but rather out in space, like the spacecraft, if it were in the vacuum, the book would just keep moving at a constant velocity, what we now call conservation of momentum or conservation of inertia. Now, Ibn Sina didn't like this idea. He didn't even like the idea of a vacuum. In the year 1000, we weren't sure whether there were any vacuums. So he put forward this idea, but it was seized upon by later thinkers. There's no such thing as natural motion versus being pushed. The natural motion of things is just to keep moving. You don't need to keep things pushed. And of course, Galileo helped develop this idea. He pointed out that if you think of the fundamental starting point of motion as constant motion with uniform velocity, and then put in things like friction and dissipation and air resistance afterward, you get a much more accurate, precise, quantitative feeling for what happens in the world. So the secret thing that sneaks in is not just a new way to torture first-year physics students with inclined planes and pulleys and so forth. There's a fundamentally new way of looking at the world. The world is not made of motions that have a mover, effects that have causes. There are things that are just doing their thing according to some rigorous mathematical laws of physics, some conservation laws very often, such as conservation of momentum. And of course, once Isaac Newton came along and put together his theory of physics and motion and mechanics, we had a much deeper version of conservation, what you could call conservation of information. And even though it's sort of in some implicit sense due to Isaac Newton, it was really Pierre-Simon Laplace who stuck his neck out and really understood the implications of Newtonian mechanics. Laplace points out the following thing. Let's imagine that we believe Newton's laws of motion, which they did at the time. And in fact, I'll point out we updated them since then, but not in a fundamentally, not in a way that really changes this particular analysis. Laplace says, look, think of two billiard balls bouncing into each other and scattering off. Now, he takes these in the tradition of Ibn Sina and Galileo and so forth to be physicist billiard balls. They make no noise, they have no air resistance, they're on a frictionless surface. So they scatter off and they go their own way. The traditional question we would ask of our students is, if you gave me the information at the start of the experiment, so where the balls were and how they were moving, I could solve the equations and tell you how they would evolve thereafter. But what Laplace points out is that, in fact, you could give me the information about what the billiard balls are doing at any moment in time. You could not only tell what's going to happen next. According to Newton's laws, you could say what did happen before that. The information necessary to tell you what's happening in those billiard balls is contained equally well in every moment of their existence. So he says, imagine a vast intellect. Later commentators thought that vast intellect was insufficiently sexy, so they said, imagine a demon, which we now call Laplace's demon. And of course, if it had been a 20th or 21st century commentator, it would have been, imagine a really big computer that knew the position and the velocity of everything in the universe and all the laws of physics and had apparently infinite calculational abilities, computational capacity. To this vast intellect, Laplace says, there is no difference between the present, the past, and the future. The future and the past are equally transparent and known as the present is because they are determined by the laws of nature. So this sets up a whole long, centuries-long debate about determinism and free will and etc. But there's something deeper that gets glossed over sometimes that is worth bringing out. It's not that anything goes, but the vocabulary has changed. Aristotle would have said if things are moving, there is something moving them, there's a cause or a reason why they are moving. Laplace says they just obey equations. What that means is that rather than a cause and effect relationship, we have patterns in the universe. Think about the integers, right? The numbers 0, 1, 2, 3, and also negative, -1, -2, -3. There's a pattern there. If you tell me any one number, if you say 3, I know what the number before that was. It was 2. I know what the number after that's going to be. It's going to be 4. But I don't say that 3 is the cause of 4 or vice versa. There's just a pattern that relates all those numbers to each other. Laplace is saying the laws of physics are like that. It's not that there's an impulse, an enchantment, a guiding force. It's just there's a pattern that says if this, then that, and vice versa. And this way of thinking about how the world works at a deep level is something we have yet to truly absorb. Of course, Laplace was not right. He didn't know about the true laws of physics. He thought that Newton's laws were more or less correct. He had every reason to believe that was true. But since then, we have relativity and quantum mechanics and so forth. So we have a better idea now of what the laws fundamentally are. In fact, one of the bold claims I want to make, and you're willing to disbelieve me if you want, but you would be incorrect, is that the laws of physics underlying everyday life are today completely known. Here, I put it on a slide just in case. This sounds very much like one of those incredibly dopey, pretentious statements that scientists have made for hundreds of years, right? Scientists, especially physicists, my tribe, are very, very famous for saying, you know, any day now, we'll have it all figured out. We'll have the theory of everything. This was especially common in the late 19th century. People were saying, yes, we have mechanics and thermodynamics and electromagnetism. Any day now, we'll have all of physics figured out. And then, of course, it all went to hell because they invented relativity and quantum mechanics and so forth. I'm not saying that. I'm not making any statement whatsoever about how close we are to understanding all of the laws of physics or everything we are made of. What I'm saying is we know some of the laws of physics, some of the things that we are made of, and more importantly, the regime that we do understand, the domain of validity of our current knowledge, includes everything in this room, includes everything that you experience in the everyday regime of your life, as long as your everyday regime is not that of an experimental particle physicist. But you are made of atoms, you are made of particles, electrons, protons, neutrons. Those protons and neutrons are made of quarks, up and down quarks. And these particles feel forces, and there's basically 4 forces that are relevant here. Gravity, pulling everything together. Electromagnetism, pulling together unlike charges and pushing away like charges. There's a strong nuclear force that binds those quarks together to make the proton and the neutron. And there's a weak nuclear force, which is almost irrelevant, except it helps the sun shine, so that's kind of important. The weak nuclear force converts protons to neutrons and vice versa by spitting out a particle called the neutrino. Okay, so 4 particles, electron, up quark, down quark, neutrino, 4 forces, gravity, electromagnetism, strong and weak, and that's it. We know there are other particles. There are muons, there are top quarks, etc. You can argue over the exact cutoff for everyday life, okay? But you're made of these particles, and everything you see with your eyes, touch with your fingers, taste with your tongue, made of these particles. And the statement I want to make is that understanding of what you're made of, the particles and the forces, the laws that they obey, is true. It's not going to go away. It's not like epicycles or phlogiston or caloric, these ideas that we had in the past that we showed later were completely wrong. It's an idea that 1,000 years from now or 1,000,000 years from now, we're still going to believe that these particles exist and that the rules that we now know are accurate ways of talking about how they behave inside you. We might get a deeper understanding. We might realize that space and time themselves aren't fundamental. We certainly don't know how to take these laws and build them up to make biology and chemistry and economics or anything like that. But at this particular level, what are the particles and forces that you and I are made out of? What are the equations that tell us how they behave? We know that. And I know that you don't believe me because I'm just showing you a cartoon. You're thinking to yourself, I am not going to believe this until I see the equation. So here you go. This is the equation. I'm very grateful to the Royal Institution for giving me these 6 hours so I can explain all of the terms in this equation in great detail. But that's okay. You don't need to know all the details. As you see from the labels on the equation, this is a single equation that more or less is the information that the modern-day version of Laplace's demon would need to tell you what happens in the world. This is the answer to the question, you tell me what the configuration of stuff in the world is right now. This equation tells you what it will be a little bit in the future, what it was a little bit in the past. It's a quantum mechanical equation. So if you observe the system, one of the things about quantum mechanics is you can only predict probabilities, not certainties. But this is the equation that tells you what those probabilities are. It includes quantum mechanics, space-time, all the matter particles that we're made of, as well as all the forces that we know about. And of course, the Higgs field lurking in the background that we finally had evidence for back in 2012. What you don't see in this picture is anything that Aristotle would recognize as a final cause or anything that Leibniz would recognize as the reason why a certain event is happening. The language being spoken here is that of patterns and differential equations, not of causes, purposes, meanings, and there's no values here. There's no judgments. This equation, what we call the core theory of physics, which has all the particle physics and also all the gravity that we know about, the core theory doesn't pass judgment on you or me. It doesn't tell us what is right from wrong. It just tells you what is going to happen. Now, even though I show you the equation, you might still not be happy because you say, well, I only trust equations that can fit on a t-shirt. So I have the experimental evidence that the core theory can fit on a t-shirt. We're in good shape. Now, I know what you're thinking. I've given this talk before in different forms. you're thinking, fine, you guys, you physicists, you have your particles and your forces, but it's just the same kind of hubris to say that we're not going to discover new particles and forces that you don't know about yet. How do you know that there's not new particles, Mr. Smarty Pants physicist? And of course, there's two answers to that. One is, it's almost certainly true that there are new particles and forces that we've not yet discovered. Remember, all I'm claiming is that we've discovered the particles and forces relevant to our everyday lives. As a working theoretical physicist, I certainly hope there are new particles and forces in understanding. I'm just saying that whatever we discover along those lines is not going to affect your biology. It's not going to affect your psychology. It's not going to affect the motion of the particles that do make up you that we know about right now. So how do we know that? That's a very grandiose claim. It's one that we really could not have made in years past. It turns out to be a very specific feature of the way that this equation works. It is based on the principles of what we call quantum field theory. Field theory is the idea that what you think is a particle, like an electron or a photon, is really a vibration in a field filling all of space. Why does it look like a particle instead of looking like a field? That's where the quantum comes in. Quantum says that when you look at these things that make up the world, they come to you in discrete packets of stuff. We call those packets of stuff particles. So quantum field theory says the world is made of fields, but quantum mechanics gives us the rules for observing them. So we can talk about them in terms of particles. And then it goes on to draw implications from that idea. So here's one simple implication of quantum field theory called crossing symmetry. This is usually taught as a little technical tool in quantum field theory, but it actually has extremely profound implications. So let's say we imagine that there is a particle or a force or a field that we haven't yet found in our experiments that might in fact play an important role in human biology or neuroscience. How would that work? Well, the first thing that a physicist would do, given the proposition that there's a new particle, is start drawing these pictures, what are called Feynman diagrams, named after Richard Feynman, my predecessor at Caltech. My most famous accomplishment as a physicist is I sit at the desk that Richard Feynman used to sit at. It is the desk given to the most senior theoretical physicist at Caltech who is not senior enough to get a brand new desk when they get there. So I got that one. And these Feynman diagrams do two things. They, number one, show us what can happen. They are pictures of actual processes. So the diagram on the left, you have an ordinary particle at the bottom, let's say a proton. At the top, the red line is some new particle, some particle that we've hypothesized. And we're imagining there's some new interaction or some old interaction, maybe electromagnetism or the weak nuclear force, via which this new particle can interact with the particle that we know about, the proton. So you read the diagram from left to right. It says that the new particle comes in, a proton comes in, and they scatter off of each other by exchanging some boson, some photon or some new boson that we haven't heard about, okay? Number one, the diagram tells you that can happen, but number two, there are rules for attaching numbers to these diagrams. So if you're a graduate student in physics, this diagram will strike fear into your heart because you go, oh no, I have to calculate a scattering amplitude, and the diagram lets you do that. It tells you the probability that two particles will come in and scatter off. Now, crossing symmetry is a feature of quantum field theory that says, given this diagram, given some new particle that could in principle interact with an old particle that I know I have inside me, I can rotate the diagram by 90 degrees. And I get a new diagram that is a little bit different. When I rotate it, time goes from left to right in these diagrams. There's a little technical rule that if a line gets flipped from going left to right to going right to left, I exchange a particle with an antiparticle. We're not at that level of detail here. But the point is that rotated diagram gives me a new process with the same probability, the same quantum amplitude as the old process has. In other words, if the thing on the left can happen, where the new particle and the old particle scatter off each other, then the thing on the right can happen, where two existing particles, two protons or two electrons or something like that, can annihilate into each other and create this new particle. You can produce the new particle. It can't hide from you. And this idea that we smash particles together and look to see what comes out and hope that new particles comes out, That is what particle physicists do. We've been smashing particles together for decades. Electrons and other electrons, electrons and positrons, protons and protons, protons and antiprotons, neutrons. We've smashed everything together that we have in the core theory of particle physics. We've seen what comes out. That's how we discovered the Higgs boson at the Large Hadron Collider in 2012. Is it possible that there are particles that exist that haven't yet been produced in this way? Sure. But we know what that would mean. Either they interact with ordinary matter so weakly that you can't make them, that you smash literally billions of particles together and none of these new particles are created. That's possible. But if that's possible, then they're not going to play an important role in you. You can't make them. They're just irrelevant to the processes that describe the atoms and the molecules inside you. The other possibility is that you do make them, but then they quickly decay away. That's what happens with the Higgs boson, for example. The Higgs boson, you make it, and then it decays away in 1 zeptosecond. A zeptosecond is a very short period of time. 10 to the minus 21 seconds. So we say we've discovered the Higgs boson at CERN. We've never seen a Higgs boson. We've seen the thing the Higgs bosons decay into. And if that's the way that these particles have avoided being seen, then again, they're not relevant to you and me. If you did have any in your brain, they would decay away in a zeptosecond or less. This is why we can make this kind of statement about our knowledge of the laws of physics underlying everyday life. It's certainly, you're welcome to imagine other new particles and forces, but if they were there and they were strongly interacting enough with you and me to be relevant to our everyday lives, we would have seen them already, and we do not. So we know what you and I are made out of. What is remaining to do is to match this underlying core theory equation to the everyday life that we see. And that's where this principle called emergence comes in. That we have different vocabularies, different stories we can tell about the world at different levels of detail. The story of the core theory with the particles, the electrons, and the quantum fields bumping into each other, that's the microscopic version of reality, our best current microscopic description. We may in the future get even deeper layers, but the layer that we have right now won't go away. And that microscopic description is a story of particles, fields, differential equations. The macroscopic world that we are familiar with in our everyday lives that Aristotle knew about speaks a completely different language. There is dissipation, there's cause and effect, there's a natural state for things to move in. There are reasons why things happen rather than not happen. And much of this is due to this first item on the list here, the arrow of time, the difference between past and future. The arrow of time is something that is absolutely central to how we think about the world. It is so central that you don't notice it is a thing. Aristotle, who wrote books on absolutely everything from metaphysics to drama, never talked about the arrow of time. Of course, the past is different from the future. That's just an obvious thing. What are you even asking that question about? But there's no arrow of time in the core theory equation. There is no arrow of time in Newton's equations for describing the world. Since the time of Isaac Newton, the best ways we have of describing the world at the most fundamental microscopic level do not distinguish between past and future in any way. Despite that, the world in which we live obviously does distinguish between the past and future in many ways. We remember what happened yesterday. We don't remember the future. I hope nobody here remembers the future. You can make choices, right? So like right now you could decide that you think this is the most boring lecture you've ever heard. You can leave. You don't need to be here for the next half of the lecture. But you cannot right now decide not to have come to the lecture. You cannot make a decision that affects the past, right? There's an asymmetry of influence. Where does that come from? If the underlying laws treat the past and future symmetrically. Well, it all comes down to this egg breaking. If you understand the egg breaking, you understand why all of these things are true. This egg breaking illustrates the increase of entropy or disorderliness, the second law of thermodynamics, which is going to be a theme of the Royal Institution's Advent calendar. Entropy increases. You clean your room, you leave it to its own devices, your room gets messier over time. That's a fundamental law of physics. Of course, you can clean it again, but that's because your room is not a closed system. In an isolated system or in the universe as a whole, entropy increases. The universe becomes more disorderly. The reason why is because there are more ways to be high entropy than to be low entropy. You give me an orderly arrangement like an unbroken egg, it is easy to break it. There's a lot more ways to arrange the molecules in the egg in the form of a broken egg or scrambled eggs than there are in the very delicately chosen arrangement of the unbroken egg. That's half of the reason why there is an arrow of time. There's more ways to be high entropy than to be low entropy. But the other half is the universe was low entropy in the past. That's more of a puzzle. Why was the universe lower entropy, more orderly yesterday than it is today? I can tell you the answer. It's because it was even lower entropy the day before yesterday. And the reason why that's true is because it was even lower entropy the day before that, and this logic goes back 13.8 billion years to the Big Bang. There's no fundamental arrow of time, or just like there's no fundamental arrow of space in the laws of physics. If you were an astronaut doing experiments, there'd be no difference between up, down, left, right, forward, backward, in front of you. You could rotate yourself out there in space, it wouldn't make any difference. Here in this room, there's an arrow of space. If I let go of the book, it falls. I could predict what direction it's going to fall in. It goes down. We don't think that's built into the nature of reality. We think it's because we live in the vicinity of an influential object, namely the Earth. What I'm telling you is that the arrow of time is exactly the same way. It's tempting, it's natural to think that the difference between past and future is somehow inherent in the nature of reality, but it's not. It's because we live in the aftermath of an influential event, the Big Bang, that had a very low entropy. It was a very organized system. We don't know why. If you want to know why, well, no one knows why. If you want to think about why, I wrote a book. That was the first book I wrote, From Eternity to Here. You can buy that. That's where this figure is from. So what this is revealing to us is that unlike an Aristotelian view, which was teleological, things were directed toward a future goal. They were headed toward going back to their natural state of being. If anything, the macroscopic world is econological, which is from the Greek word start or beginning. The special state of the universe was where it began. We don't know why it began in such a special state, but since then, it's just been winding down. That's all it's been doing. There is no future goal or place toward which we're going. That increase of entropy is sufficient to explain all of the differences between past and future. And we can't go through all of them. That would require another book or another lecture. But let's think about the idea of a memory or a record. Some artifact, some feature of the present day that gives us knowledge of the past in a reliable way. So maybe that's literally a memory in your head. Maybe it's a photograph. Maybe you're walking down the street and on the sidewalk you see a broken egg. I claim that the evidence that you have, there's an egg broken on the sidewalk, gives you different leverage over the past than over the future. You can ask yourself, what does the future of the egg hold? Well, many things are possible, right? It could just sit there, someone could clean it up, a dog could come by and eat it, it could be washed away. There's many different possible futures. What was the past of the egg probably like? Well, with very large probability, there was an unbroken egg and somebody dropped it, right? We can say something much more specific and informative about the past, given this evidence of the egg right now, than we can about the future. Why is that? Again, if all you knew were the deepest laws of physics, that equation I showed you, or Newton's laws or whatever, your ability to extrapolate toward the past and future would be identical. You have some knowledge of the world's present state, but it is incomplete. You have this macroscopic configuration of the egg, but you don't know what all the atoms and molecules are doing. The number of things the egg could possibly do toward the future is exactly equal to the number of things it could have been doing in the past, if all you know is the fundamental laws of physics. But you know something else. You know that the early universe had a low entropy. You know that our past, something that philosophers have sadly labeled the past hypothesis, which is the most boring label I've ever heard, but the past hypothesis says the universe started with low entropy. And that provides an anchor, that provides an asymmetry between what we know about the past and what we know about the future. So you have not only the present information, but also that past anchor, and that lets you infer features of what actually happened in the past. If you have an egg broken on the sidewalk, there used to be an unbroken egg. If you have a photograph of you, 10 years old, wearing a red sweater, you probably were wearing a red sweater that day. We all know that we've all heard, right, that there's this general tendency of the universe to wind down and evolve toward its heat death over time. And there is, in my country, there's a controversy over what is called creationism. Some people think that if you think that there's a fundamental feature of the world where things just go to more and more disorderly states, that is incompatible with the appearance over cosmological history of things like you and me. Because we're not low entropy, how is it possible that such highly organized things like you and me could just pop into existence in a world that is generally becoming more and more disorganized? And scientists have an immediate glib answer to this. The Earth and its biosphere is not a closed system. It's not isolated. You can clean your room. There are things called refrigerators. If you put your bottle of champagne in the refrigerator, its entropy will go down as it cools, okay? So therefore, there's no contradiction with the second law of thermodynamics that low entropy things like you and me came to be as the universe expanded and cooled. On the other hand, just because you can clean your room doesn't mean you will clean your room. Some of you may have experienced this with children or even yourselves. So the fact that the Earth is not a closed system allows for the appearance of organized systems like you and me, but it doesn't explain why it happened. The explanation is, of course, incomplete. We don't know the full answer, but it relies on the fact that there's a difference between simplicity and complexity. There's an axis, if you like, between simple systems and complex systems, another axis between low entropy organized things and high entropy disorganized things. Being disorganized does not mean being simple or being complex. Think about one of my favorite examples, mixing cream into coffee. On the left, you have a low entropy situation. All the cream's on the top, all the coffee's on the bottom. As time goes on, the cream mixes into the coffee. On the right, you have a high entropy situation. Everything is mixed together. That's a natural flow of time from past to future. But think about the system on the left. It is very simple. Here, the technical definition of simplicity versus complexity is, how long do you have to talk to me to describe the system in full detail? How many bytes of information do you need? On the left, all the cream's on the top, all the coffee's on the bottom. It's very simple. On the right, everything is mixed together. It's also very simple. It's in between. It's where those tendrils of cream and coffee are mixing together in some intricate fractal pattern. That's when things look complex. So there's a natural tendency, as the universe ages, for entropy to increase. But at the same time, complexity first increases and then decreases. It's not only that complex systems are allowed to come into existence when entropy is increasing. In a very real sense, they do come into existence because entropy is increasing, or at least they can maintain themselves. They can maintain structure and order and self-repair because we're in a very low entropy universe that is only gradually becoming more and more disorderly. And it's not just cups of coffee and cream that this is true for. This is true for the universe. So here is the history of our observable universe in a very brief presentation. It started out, we don't know what happened at the Big Bang, but 1 second after the Big Bang, we know what the universe was like. It was hot, dense, and smooth. That's it. That's a very simple explanation, a very simple description. I didn't take that many bytes to give it to you. As the universe expands and cools, it becomes increasingly lumpier because gravity pulls things together. So a few 100,000 years after the Big Bang, we get the cosmic background radiation, a snapshot of what the universe looked like when it first became transparent. Tiny variations in density from place to place, but still pretty smooth. Now, 14 billion years after the Big Bang, the universe is very complicated. We've formed galaxies and stars and planets and biospheres and lecture halls. It's a very complicated part of the universe. But we can keep going. We discovered in 1998 that the universe is not only expanding, but accelerating. It's expanding faster and faster, which means it's never going to stop, according to our best current theories. What will happen is the stars will burn out. 10 to the 15 years, 1 quadrillion years from now, the last star will stop shining. Sorry. All of those stars are going to fall into black holes. And Stephen Hawking taught us in the 1970s that even black holes don't last forever. They give off radiation. So 10 to the 100 years from now, what used to be called a Google, before the search engine took over the term, 10 to the 100 years from now, there'll be nothing left. in the observable universe. There will literally be nothing but empty space. Nothing but empty space is very simple, but it is very high entropy. Everything's very far apart, so there's lots of different arrangements for the things that do exist in the universe. So the entropy of this universe just increases, but the complexity first increases and then decreases. This is a natural, robust, generic way that complexity can come into being. What we want to do, that's the easy part, what we want to do is take that natural, robust, simple story and apply it to the real evolution of complicated structures like life here on Earth. So for me, the epiphany was one day I was taking a plane ride to a conference, and I was actually interested in the origin of life. I was reading a paper, a technical paper on the relationship between physics and the origin of life. So I'm sitting there reading my paper. The guy in the plane seat next to me starts talking, and you know, as a theoretical physicist and cosmologist, you meet a lot of people who have theories about the universe that they would like to explain to you. So this guy looks at my paper and he says, oh yes, I'm familiar with that work. In fact, I can tell you the purpose of life. I'm like, okay, long plane ride ahead, lay it on me. He said, the purpose of life is to hydrogenate carbon dioxide. Not what I expected his theory to be. Turns out, the guy sitting next to me was Dr. Michael Russell of the Jet Propulsion Laboratory in Pasadena, one of the world's leading researchers on the origin of life. What are the odds? It turns out we were going to the same conference, so it's not completely a coincidence. Everything happens for a reason, remember. So Mike Russell's theory, which is not universally accepted, we don't know how life began. There are different competing ideas. He has one of the good ideas. His idea is that in certain environments of the early Earth, we're in a low entropy configuration. In particular, all the carbon atoms were in the form of carbon dioxide, which happens to be relatively low entropy. Given all the water and hydrogen around them, they could be in the form of methane, CH4. That would be a higher entropy configuration. In some sense, to be a little bit poetic about it, it wants to be in the form of methane. That would be higher entropy. But there is no simple chemical reaction that goes from carbon dioxide to methane while increasing the entropy all along. There's a barrier in between. You need to first lower the entropy to get to the higher entropy state. So Mike Russell's idea is that even though there's no simple chemical reaction, there is a network of complex chemical reactions that could do the trick. And that in the right circumstances, that could happen and be self-sustaining. And that self-sustaining metabolism could then break free of its original environment and become the precursor to life. So it's more than just a pretty story. He actually made a prediction. He's a geologist by training, and he said, you know, if this is true, there must exist under the ocean floor certain kind of geological formations, warm, alkaline hydrothermal vents, where this kind of chemistry is going on. And after he made the prediction, they found them. This is what you live for in science. This is a picture of the Lost City hydrothermal formation deep underneath the Atlantic Ocean in the mid-Atlantic ridge. It lasts for tens of thousands of years. So Mike Russell and other people think that maybe this is the kind of place where life began. We don't know. I'm not pushing this theory necessarily. What I'm pointing out is that rather than saying, but entropy increases, why should something as complex as life ever come to be? It's very, very plausible that the appearance of life depended on the fact that entropy tends to increase. So you actually find the complexity depends on entropy increasing, and vice versa. The reason why entropy could increase in this system is only because you had a complex network of reactions. And that, of course, continues to the present day. We live in an open system. We live here on Earth. You ask yourself, what good is the sun? What does the sun do for us here on Earth? You might think, well, we get energy from the sun, but that's not quite right. It's true that we get energy from the sun, but we give the same amount of energy back to the universe. We radiate back into the universe the same amount of energy that we get from solar radiation. The difference is that for every 1 photon of light we get from the sun, visible light, we radiate 20 photons of infrared light back to the universe, with on average 1/20th of the energy each, but 20 times the entropy. The thing that the sun gives us is not just energy, but energy in a concentrated low entropy form. And we then photosynthesize, chew our cud, eat our cows, give lectures, write books, all of that, all of those processes increase the entropy of the universe along the way, and then we give it back to the universe in the form of infrared radiation. So we are sustained by increasing entropy. Back in the 1800s, it was a reasonable hypothesis that life was a thing. We thought, for instance, that heat was a thing. If you put a hot object next to a cold object, they equilibrate. They come to the same temperature. So people said, well, that's kind of like putting two vessels with a fluid in it. The fluid comes to the same level. There must be a heat fluid that flows from the hot thing to the cold thing. Not true. Don't believe anything I just said. Heat is not a fluid. Heat is a feature. It is a way of talking about the motions of the atoms and molecules. Life is the same way. Life is not a force or a substance that is in your body and then leaves. It is a feature. It is a way of talking about what is happening inside you. The bad news is that that means it will end someday, but we'll get to that in a second. I have lots of bad news. Don't worry. The good news is that once this happens, once you get life, once you get this chemical reaction that sustains itself and reproduces and wants to keep going, there's this wonderful thing that kicks in called evolution. If there's different ways the chemical reaction could arrange itself, and some of them are more robust and more likely to survive, Professor Darwin would tell you that's what's going to happen. Those more robust ones are likely to dominate the future ecosystem in that particular environment. And what that means is that we can, once again, change our vocabularies. Just as we change our vocabulary to going from particles and atoms to eggs and entropy and time, we can change our vocabulary when we start talking about biology and evolution. Because the new words that creep into our vocabulary are words of purpose and reasons why. Why is it that a giraffe has a very long neck? You could say, if you want to be annoying about it, well, because of the laws of physics and the initial conditions of the universe. That's why giraffe has long necks. That's the answer to every question. Why is something true? The laws of physics and the initial conditions of the universe. But it's not the only possible answer. And in fact, it's not a very sensible answer, right? There's another answer that says, well, giraffes had mutations in their genes, and some of them got longer necks, and those were able to reach sources of food up on trees that other animals with which they were competing were not able to reach. And therefore, over successive generations, the longer and longer necks survived and flourished, and they were naturally selected to be like that. So in a very real sense, the purpose of the giraffe's long neck is to help it reach food sources that it couldn't otherwise reach. Where did that purpose come in? Did someone put it there? No, it evolved naturally. But that doesn't mean it's fake. It doesn't mean it's an illusion. It is a useful emergent vocabulary for talking about what happens at the macroscopic level. And you're probably willing to believe that if I'm just talking about life and biology. It's where it comes to thinking and neuroscience and consciousness that people tend to get off the bus. And of course, just like with the origin of life, we don't understand the origin of consciousness or what it really is. What we can do is suggest occasional steps in the history of life which might help us understand why consciousness became an interesting part of biology. This guy up here, the C. elegans nematode, a kind of flatworm, is a little model organism that biologists like to study. In your brain, the cells doing the thinking are the neurons. There's something like 85 billion neurons in your brain, and different neurons are connected to each other. And a big project for modern neuroscience is studying the connectome, the way that all of the neurons in your brain are connected to each other. We're going to start with a simpler system. We're going to start with C. elegans. We have its connectome. We've mapped it out. A C. elegans flatworm has exactly 302 neurons, so you can actually count them. And then, now we've counted them and see how they connect to each other, we're trying to figure out what they're for, what they do in the flatworm. There is a paper that came out. I'm not sure if it's correct or not. Theoretical physicists, remember. But there's a claim that is a very interesting one that says they can identify one of those neurons whose job it is to tell the nematode whether it's looking at itself or the rest of the world. Is this thing in front of me, is this dirt, is this water, or is this just my tail, right? This one part of one neuron, its job is to sort of have a little bit of self-awareness a little bit of, well, this is me, not the rest of the world. And you can see why, if that developed just through natural fluctuations and mutations of evolution, it would be an advantageous thing to keep around. We have much more highly developed self-awareness, and you can imagine other steps along the way. Malcolm McIver, who is a mechanical engineer at Northwestern, he studies fish and how, in particular, fish sense their surroundings. So he points out that a fish with its eyes are very ubiquitous in life. They develop multiple independent times in the course of evolution. But eyes aren't that great if you're underwater. You know, you can see tens of meters at most. The attenuation length of light is just not that far. And you're swimming at meters per second. So if you're a fish, every time you see something new, you have seconds to react to it, maybe a second, right? So the evolutionary pressure is to make a decision really quickly. Is this food, is this friendly, or is this foe and I should run away? So you don't need to think too much if you're a fish. But when you hop onto land, now the attenuation length of photons is kilometers. You can see off to the horizon. You can see essentially forever. It's possible that you now see something coming long before you need to react. So there's a new evolutionary pressure that starts exerting itself that if you, just through the randomness of evolution, develop the ability to contemplate different hypothetical scenarios, then you have a new way of winning the struggle for survival. That is to say, up on land, it pays to develop an imagination, not just an awareness of yourself, but the ability to put yourself hypothetically into different situations and say, what is the right thing to do? We don't know if any of this is right, okay? We don't know how consciousness evolved, or even we don't even know the right definition of consciousness. But you can imagine stories like this will be put together by the progress of biology and neuroscience over the years. The only thing that I really care about, that I really want to stress, is that there's nothing that we know about consciousness that is incompatible with the idea that we are made of the particles and fields of the core theory obeying that equation. Here I have a picture of my brain. This is actually it's not my brain, it's the skull. So I was it's not to scale either, but I was in a machine, an MEG, magnetoencephalogram machine, and there were sensors placed on my skull that looked for magnetic fields. You've seen fMRI pictures, which are very, very good at locating things spatially in the brain, but their time resolution is not very good. And MEG has great time resolution because what happens is your brain is made of particles in the core theory, and that includes your neurons. And when your neurons talk to each other, electrically charged particles race down the neurons. And as people who stood at this desk long before me could tell you, when charged particles start moving, you create a magnetic field. So this senses the magnetic field. Those blue and red splotches are the magnetic fields, the south and north poles, coming in and out of my skull when I think a thought. This is just a reminder of something you already know, which is that thoughts are associated with real physical things happening in your brain. They're not abstract things outside our physical bodies. There used to be a theory that they were, right? René Descartes, very famously, promulgated a theory of mind-body dualism. He was a skeptic, and he came up with a cogito ergo sum argument. I think, therefore I am. I cannot doubt the existence of my mind, because it is the thing doing the doubting. But he says, it's very easy for me to doubt the existence of my body. So if I can doubt the existence of my body, but not the existence of my mind, they must be two separate things. He wrote books about this, became very famous, died a tragic death in the cold, but that's a whole other story. So there weren't a lot of tenured faculty positions at the time of Descartes in the 1600s, so one had to be nice to potential patrons. So he got to know this young lady, Princess Elizabeth of Bohemia. His aim wasn't very good. They were in exile and didn't have a lot of money, Princess Elizabeth and her family. But fortunately, Princess Elizabeth was a genius. She was a wonderful thinker, very highly educated. She devoured Descartes' books, and she didn't agree with what he said. And they struck up a correspondence, which is a wonderful thing to read. I encourage you to go look up Princess Elizabeth's correspondence with Descartes. And Elizabeth says, look, this mind-body stuff, I just don't know. You're saying that there's a mind that is literally immaterial, that has no location in space, and yet it clearly influences what our bodies do. When I talk, presumably my mind has something to do with the words I'm saying. So Elizabeth wants to know, how does the immaterial mind causally affect the material body?
And Descartes, in response, drew pictures like this. This is, it was back in the days they were just beginning to open people up, right? So they knew that your brain came in two different hemispheres. There seemed to be one organ in the brain that there was only one of them. It was not broken in two. That was the pineal gland, that little teardrop-shaped thing right there. So Descartes says, well, you only have one mind, one soul, so I bet that the soul talks to your body via the pineal gland. Yeah, no one else believed it either in the 1600s. It was not a very effective hypothesis for understanding what was going on. And so Elizabeth kept pushing on him, and he never really gave a very good answer. Today, we would have a much sharper version of Elizabeth's question. Remember this. I know you love this equation, right? If Princess Elizabeth were here today, she would say, Renee, tell me how the immaterial mind pushes around the quantum fields of the core theory. This equation tells me what's going to happen in the quantum fields of the core theory without any reference to an immaterial mind, so you must be saying this equation is wrong in some way. Tell me how. And there's still no answer to that. So the conclusion that I want to draw is not that I understand what consciousness is or how it came about, but that we should be able to understand it without invoking violations of the physical laws that make up you and me. Does that mean that we are non-autonomous robots? Well, I don't think so. So the philosophy that I try to elucidate in the book is called Poetic naturalism. The idea is that naturalism says there's only one world, the natural world. But poetic means there's many ways of talking about the world. There's many different levels of description, whether it's atoms versus gas in a room, or emergent purpose for the neck of the giraffe, or even things like making choices. You can describe yourself as a set of particles and forces obeying the core theory, or you can describe yourself as a person. And people make choices. If you choose to describe yourself using only atoms and molecules, then there is no such thing as free will, and there's no such thing as the ability to make a choice. But if, as real, actual people do, you describe yourself as a person, then you can't help but attribute to yourself the ability to make choices. So if you want to say, can free will, the ability to make choices, be real and true even though we are made of atoms? Yes, of course it can. In the same way that any emergent property can be real. The different vocabularies work within themselves. You can't start a sentence in one language and then end it in another one. And once you accept that, then the same thing goes true for more judgmental, value-laden propositions. Is there right and wrong? Is there a way to live in the world with meaning and compassion? Well, yes. It's nowhere to be found in the fundamental atoms, but nowhere to be found in the fundamental atoms are tables either, or water, right? These are higher level emergent properties. And caring and meaning and purpose are the same kind of thing. Now that bothers people because they want things like right and wrong to be objective, right? Even the most hardcore, scientifically minded person wants to say, well, I will someday do so much science that I will tell you right from wrong. I will discover how to live as a human being. And I'm here to say that is never going to happen. More bad news, sorry. The good news is that you can choose what to label right and wrong, and no one can stop you. You construct your own morality. The analogy I like to use is think of the rules of chess. The rules of chess are not fixed by the laws of physics. We made them up. We all agree on that. But that doesn't mean they're arbitrary. That doesn't mean you could make up any old rules and they'd be just as good. When we made up the rules of chess, we had goals in mind. And when we make up the rules of right and wrong and living together in the world, we likewise have goals in mind. We will not always agree. There will always be people who would rather play Go than play chess. We might have to sort of come to an understanding of what our overlap is, but that doesn't mean that we're adrift. It doesn't mean that just because the universe doesn't tell us how to behave, there is no way to behave. All right, the final piece of bad news, I already sort of foreshadowed this, but you are all going to die. So biologists like to study these scaling relations, how one biological property depends on another one. So it turns out that larger animals live longer, but their hearts beat slower. And in a particular kind of animals, like mammals, for example, these effects cancel out. In mammals, very roughly speaking, every mammal is granted 1.5 billion heartbeats for their lifetime. On this axis, you can figure out, you tell me how heavy an object is, a mammal is, I will tell you how fast its heart beats and how long it's going to live. Now, we human beings, heartbeats at, once per second, right, 60 or 70 times a minute, so that puts us at about 40 years. And that's about right. That's how long we used to live back in the state of nature. Of course, these days we have Obamacare and the national health and pasteurized milk. So we have increased our lifespan. We live twice as long as we should. So that gives us 3 billion heartbeats to our lives before we die. And if you believe in the core theory, if you believe that we are made of particles obeying the laws of physics, then there's no life after death. There's no place for the information that is contained in your neurons to go when you die, because it's in your neurons, it's in the atoms that are there, they stay in your body, even when you die. And that can be sad. You might want to I would have liked to live, not maybe forever, forever is a long time, but I think I could keep things interesting for a few 100,000 years before they got boring. I only get 3 billion heartbeats, and 3 billion is an interesting number. It's sort of a big number, but it's not that big. I mean, you've squandered a couple thousand heartbeats just over the course of this lecture. Knowing that you have about 3 billion heartbeats allocated to you makes every heartbeat seem precious, right? It's not just like a little thing that will grow into something after we die, because this is it. Every one of those heartbeats is meaningful to you because you only have a finite number. So the good news, this is not going to sound like good news after all that bad news, but the good news is, on the one hand, we are very, very small. Okay, this is the famous Hubble ultra-deep field, an image of galaxies. If you take a telescope and point it at the sky, and you click the shutter on the camera and you just leave it open, this is what you will see. If your telescope is the Hubble Space Telescope, this is what you will see. Our universe is alive with galaxies. Our galaxy, the Milky Way, has about 100 billion stars. Before last week, I was able to say there's about 100 billion galaxies in the observable universe. I don't know if you're following the news, but they discovered that the density of galaxies is actually 20 times higher than we thought it was. So there's about 2 trillion galaxies in the observable universe. Every one of these dots, even the tiny dots, that's a galaxy with 100 billion stars. Who knows how many royal institutions they have where there's a lecture going on there with a picture of us up there. We seem very small. That's the last piece of bad news. The good news is we took this picture, right? Exactly, there you go. Appreciate the good news. We are very, very tiny, insignificant. The universe is not about us. If the universe was about us, if there was some purpose to the world that was for our greater glory, we would not be around a medium-sized planet, around a medium-sized star, in a galaxy with 100 billion stars, in a universe with 2 trillion galaxies. We'd be more central. And if you look at the ancient pictures of the world, we were always much more central than the modern view had it. Despite that, we are the little part of the universe in this age when things are complex and interesting that has developed the capacity for self-awareness and reflection and thinking and rational thought and writing books and buying books, by the way. And that should make us feel pretty good. We don't always do very well at it. I think both in my country and yours, there are examples in recent political history where things have gone not right. But we have the ability to be rational, to think, to invent, to discover, to create new things, to care about each other in ways that other parts of the universe just don't care about each other. And that's that capacity that we have, as fleeting as life is, it's up to us what to make of it. The fact that we are made of atoms and particles obeying the laws of physics doesn't stop us from caring about ourselves, the rest of the world, our legacies, the people next to us right now. So that's a choice that we can make, completely compatible with the laws of physics. I urge you all to choose very wisely. Thank you.